Okay, good afternoon. Now I will present about our mini project for our control system. So at first we introduce about our team member. My name is Eugene. My matrix number is 211022106.
My name is Nafataya Tunashira binti Ismail. My number matrix 2110220093.
My name is Nur Afika binti Anizan. My matric number is 211022094.
So in our mini project, we will use two compensator, which is lead compensator and the lag compensator. So now I will introduce about the lead compensator. So the lead compensator is used to increase the response speed of a control system while maintaining the stability. So lead compensator is introduce a fed lead to the system transfer function. Anticipate the system response and help it to reach the discrete output more quickly. It reduce the settling time and increase the stability margin. So it enhances the stability and steady state accuracy of the control system. So next our part, so the lag compensator is used to improve the steady state accuracy of the control system. It introduces a fed to the system transfer function. So it slows down the system response and providing more damping. It will reduce the overshoot and improve the system stability and improve the tracking accuracy and the stability of the control system.
I would like to explain about the second question, which is how to improve 10% using lead compensator. This phase margin we got here is from the first board plot, which is negative 56.44. As you can see here, we got negative 56.44. And then the gain crossover frequency here, 1.6818. We got it from the first board plot here. And we convert it into the radian over second, which we got it 10.57. And we want to improve 10% from the phase margin. We calculate it, we got the new phase margin, negative 47.084. This we plus 15 because it is safety margin. And the value we got, we put into the phase margin formula, which is phi max equal to sine negative 1. We multiply by alpha plus 1 over alpha negative 1. And we got the alpha value 0.15. The alpha value that we got 0.15, we put it into the gain crossover frequency formula, omega n equal to 1 over tau square root alpha, which we will get the tau value 0.244. And from this value, we put into the new transfer function formula. We got the new transfer function 1 plus 0.0366s over 1 plus 0.244s. For the lead compensator, we for the lead compensator, this one we use the first board plot, which is the k value is negative 10 and the 0 is 3 and negative 6, while the pool is negative 2, negative 3 and negative 4. This one is the new numerator which we got from the calculation, 1 plus 0.0366 s, and the new denominator is 1 plus 0.244 s. And then we insert it into this line, and then we will generate the phase margin and gain crossover frequency. The new phase margin is negative 76.081 and the new gain crossover frequency is 0.9952. Now we look at the graph. At 0 axis, we get the gain crossover frequency 0.99, which is the same as the one that we calculate, 0.99, and the new dB is 10.2 dB, which is it increased from the first board plot, and at the negative 180 axis, we get the phase crossover frequency is 0.4499.
Afika already told about lead compensator, and now my turn to share about lag compensator. For the lag compensator, we also need to calculate the alpha and also the zero and also the tau. For the firstly, we need to find the phase margin from the first board plot. Then we got negative 56.439, and then we see the gain crossover frequency. We got 1.6818. So the question need to improve 10% from the old crossover frequency. So 10% multiplied by phase margin negative 56.439. We got the value after the multiplication. We got negative 5.644, and then plus by the old phase margin negative 56.439, and then plus by 5 is for safety margin. And after we got negative 57.083, we need to minus by 180, and then we got negative 237.083. From the graph at negative 237.083 is equal to 1.71 Hz. 1.71 Hz we need to convert to radian, and so we need to multiply by 2 pi. 1 rad is equal to 1 pi, and then for get 1.71 Hz in radian, we need to multiply by 2 pi, and then we got 10.7 rad per second. From magnitude graph at 1.71 Hz, we got negative 0.1545 dB. So to calculate the alpha, the equation is dB is equal to 20 log alpha. So we have the value of dB, negative 0.1545 dB, anti-log by this value, and we got 1.99. So here the Scilab of this lag equation. We got the new transfer function. By the way, we need to find the zero first. 10.7 is divided by 10. We got the 0, 1.07. And then the value of 0, we can find the value of tau. The equation for tau is equal to 1/7. And then we got 0.90 for the tau. For the new transfer function for lag compensator, the equation is 1 plus tau s over 1 plus alpha tau s. So we put the value that we have calculated. We got 0.93 for tau and 1.99 for the alpha. After we calculate, we got the new transfer function 1 plus 0.93s over 1 plus 1.85s. So we can see here. So after we calculate, we can make a new board plot. So for the numerator, this we use the old one, and the numerator we also use the old. And for the new transfer function, we declare as num_c for the numerator. The numerator is then c, and then this is the new transfer function we use. G is equal to numerator new over the numerator new multiplied by numerator old divided by the numerator old. So for the transfer function, this is the new transfer function. We got the phase margin negative 31.92, and again crossover frequency we got 0.908. Now we see the both plot for the new transfer function. It already generated for the new one.
In conclusion, so a lead compensator increased the phase margin by introducing a zero before a pole. So by appropriately placing the zero in the poles, the phase shift introduced by the compensator can effectively increase the phase margin and improve the stability of the system. So design a lead compensator is best compensator to as the phase margin compared to the lag compensator. So typically the lag compensator parameters are determined through the combination of the analysis and the experimentation. By adjust the zero and the pole location, we can tailor the lead compensator to provide the discrete phase margin improvement. However, it is important to note that there is no a direct one-to-one corresponding between the phase margin improvement and the compensatory parameter. The compensator design involves the trade-off between the phase margin improvement, stability, and other performance and requirement.